Good afternoon and welcome to the CERIAS Computer Security Seminar from Purdue University. Our speaker today is Dave Keppler from the MITRE Corporation. His topic will be transforming applications for vulnerability resilience. Dave?
Thank you. I'm going to be giving a talk about some research I'm doing at MITRE. General problem we're trying to solve is lots of applications out there, lots of vulnerabilities in them, people attack them all the time. The main problem is attackers can predict what you're running, they know what software you have, they can test offline, craft their exploits as much as they want until they finally get something that works, and they can use that same attack to compromise a wide range of systems across an enterprise. So our current defenses today are inadequate in this kind of an environment. A lot of things like our antivirus software and IDS filters, they're trying to search out bad things that we know about. Won't catch new exploits, won't catch very targeted single-use exploits. As well as after that is trying to write software that simply has less vulnerabilities in it. Well, that's pretty slow, very expensive, doesn't do anything for the software that's already out there. And also related to that is this idea of a patching treadmill, constantly trying to catch up to where the attackers are, trying to stay ahead of what they know about the exploits. And other things, brittle perimeters like firewalls, VPNs. All an attacker needs to do is find one way around that, and then they have full access to your systems. So observation that I've made is these actual vulnerabilities are pretty constraining on the attacks. The attacks themselves are quite fragile and rely on predictable attributes of software. Things like memory addresses, location of data structures, how the stack is constructed. A good example is the classic stack smashing code injection vulnerability. So we have a picture of a stack frame of a function on the stack, return address, some local variables, and some buffer. An attacker can overflow this buffer if they know where that buffer starts, how long it is, and where the return address on the stack is. They can craft this overflow in such a way that they can cause the function to execute the code that they've injected. The reason why this works is because they can predict those two things, where the buffer is, where the return address is, how much do they need to overflow. But none of those specific factors are implicit to the higher level functioning of the application. There's just implicit things that were picked by the compiler when the software was compiled down into machine code, or attributes of the platform that the code is running on. So our objective in this project is find ways to break those assumptions. We can perturb an application in small, relatively inexpensive ways, leave the application functioning identically. We'll change it just enough that it breaks attackers. Eliminates their ability to make assumptions about the state of your software. So there's been a fairly large amount of related work in this field. A lot of it stemming from the old fault tolerance work, Byzantine fault tolerance, isolating parts of a software, things like sandboxing, or old idea of multi-version programming, have separate teams write a piece of software to the same specifications. Ideally, they'll come up with different implementations that have different flaws. It won't fail in the same ways. A lot of hardening techniques out there, things like bounds checking on buffers that Java and C# and other languages like that use. The no execute bit on the stack to prevent the stack being treated as executable code. Other types of stack protections, implementing stack cookies, checking that they haven't been overwritten before you return, and other ways of reordering the way the stack is laid out in memory. All of these are things that can only be applied at compile time. The actual randomization factors, where they do exist, are fairly static. May only be chosen once when a program is actually executed. And also another idea is just general diversity randomization, obfuscating the code. So we have address space layout randomization, changes where the stack begins in memory, where the heap begins in memory, or where libraries get loaded. Also another idea of instruction set randomization. You actually encrypt, transform the code of a function, dynamically decrypt it as it's executed. When an attacker doesn't know the correct execution key, they won't be able to inject code that decrypts properly into what they need. Another idea we've made use of is invariant programming. It's kind of a modification of multi-version program, like I mentioned before. But instead of having separate teams, we take one piece of software, transform it using some artificial transformation engine, run each of the variants in parallel given the same inputs, compare the outputs, and if there's any kind of divergence, we know that an attack is probably underway. We make changes to the program so an attack can only work successfully on a single instance at once. So what we've been doing in this project is trying to extend that prior work. A lot of it's only focused on one type of vulnerability, usually code injection, and a lot of it only works at compile time. So what we want to do is defend against many different types of vulnerabilities. Code injection, obviously. We also want to deal with command injection, a good example of that being SQL injection on web applications, and also more generic attacks which just overwrite data within a program, like a privilege escalation that, say, overwrites the effective user ID of a session. And finally, we want to apply these defenses to existing programs. So if we're limited only to defending new programs, there's an enormous base of software that still remains undefended. So existing approaches, like I said, we have source code, compiles down to machine code, one piece of machine code distributed all over and executed. So whenever there are any kind of defenses, they're only injected one time and remain the same after. So what we're doing with this project is introducing a couple of extra steps into this deployment. So we have source code compiled down into machine code. We take that binary machine code, analyze it, and transform it. So we can do control flow analyses and data flow analyses on the program given its binary instructions, determine where data structures are, where the code is, how the stack gets constructed, and find ways to change that without altering the high-level functioning of the program. So one thing we've done is addressing SQL injections in Java web applications. So this kind of command injection occurs when a program has some embedded command language in it that's interpreted, and those commands get passed out to, say, a database or a command shell, things like that. And the general problem in this case is usually that the inputs from the user aren't filtered properly, get plugged straight into this embedded commands and executed. So if an attacker knows what your command looks like, what the syntax of that command language should be, they can alter the intent of the actual query. So in this case, I have, say it's a standard username password kind of check in a web application. The attacker enters their username and a password. Poorly implemented code would just take those and plug them directly into the query.